In this video, we are going to solve Project Euler problem 47, distinct prime factors. So the problem statement is the first two consecutive numbers to have two distinct prime factors are 14 and 15, as you can see. 14 has two prime factors, 15 has two prime factors, and 14 and 15 are consecutive. The first three consecutive numbers that have three distinct prime factors are these numbers. So 644 has prime factors 2, 7, and 23. And the next two numbers also have three distinct prime factors. Now the problem is that we need to find the first four consecutive integers that have four distinct prime factors each. And more specifically, we need to find the first of those numbers. Okay, so let's jump right into it. We can solve this problem in a relatively straightforward way. We are going to enumerate all integers, check for each number whether or not it has four prime factors, and if we encounter four of those numbers consecutively, then we will know that we have found numbers that fulfill this property. Okay, so I am first going to have a method that takes an integer and returns a boolean. So I will call this function has four distinct prime factors. So this takes an integer and outputs a boolean. This is a predicate. And now, how would we implement this? So we could go ahead and iteratively divide the number that we get. So let's call this number n. But this would be a very inefficient process. It is much better and also much faster to make use of prime numbers, to pre-calculate a list of prime numbers that we can check against. So, well, the task of generating prime numbers has already been solved, so I won't cover this in the video. I will instead just copy this function from the Haskell wiki. This function implements a prime sieve, a sieve of Eratosthenes, which gives me the first n prime numbers, a list of the first n prime numbers. So let's just paste this in. Minimize that because it is not important. And now we have the function primes to ua with the argument top, which gives us all prime numbers that are less or equal, I think, than top. Okay, let's add the list of prime numbers as an argument here. So list of prime numbers, I will call this primes. And now let's check whether or not n has four distinct prime factors. For this, I will first filter the list of primes that I have. So I will take from the list of primes all numbers that are less or equal than n divided by 2. Div 2. Why am I doing this? Well, because a factor of n has to be less or equal than n. N divided by 2, of course. So basically this allows us to drop most of the primes. We don't need to check against primes that are larger than n because they cannot be a factor of n. So now let's filter for all the primes for all the remaining primes that divide n. So let's filter by p. So p is accepted if n mod p is equal to 0, if we can divide it without remainder. Okay, so now this expression gives us a list of the prime numbers that divide n. Okay, but we actually only want to know if there are exactly 4 of such primes. So what we are going to do to find out whether or not there are 4 of those is we're going to take 5. Take 5 will have the effect that first we will only ever evaluate the first 5 elements of this expression, which is good for efficiency. But also, if there are less than 5 of those prime factors, this will return a list of length 3, or 2, or 1. So let's take the length of this and check whether or not this entire expression is equal to 4. Okay, so we have our has 4 distinct prime factors function. Now the rest is easy peasy. Let's start with our main function of type IOUnit. So the idea is that we map the has 4 distinct prime factors function to all the integers. Okay. Then, because this gives us a list of Booleans back, we need to zip this with the integers again. So this basically gives us a list. Let me just write this here as a comment. This gives us a list of the form int bool, tuple int bool, where int is an integer and bool states whether or not the corresponding integer has 4 distinct prime factors. And now we need to find the first of occurrence in which 4 of those numbers appear consecutively. So I will call this function find first 4. We will write this in 1 second and then print this. Now, of course, I forgot to add the list of primes here. So let's just give this argument and define it here in a where clause, so we can be sure that it is only evaluated once. Prime is UA, and let's calculate the primes until 100,000. I think this should suffice. Okay, so now we are missing our find first 4 function. Find first 4. This, of course, should have the signature tuple int bool 2 int, because we want the first number or the first number in the of the first occurrence of 4 consecutive numbers that have 4 distinct prime factors. Find first 4. And now we can of course solve this or write this function recursively. I will do this as follows. So let's call the argument ls for list, and if we take the first 4 from the list and only consider the second element, so map S and D, which now gives us a list of booleans. So 4 booleans would indicate that the 4 first elements of the list here of ls fulfill our property. So if this is equal to 4 times true, or a list of 4 true values, so replicate for true, then we have found the first occurrence of well, the property we're looking for, and can just return, well, what do we actually return? We return the first element. So in the first element of our list, we return the, well, first value of the tuple, so the integer. This can be written as, so this is our tuple, x, the first element is x, the second element is not cared about at all, and for now we also don't care about the rest of the list. So, okay. Now, if this here is not the case, if there are no 4 consecutive numbers that fulfill the 4 distinct prime factors property, then otherwise we just keep looking. So we call the function recursively. Let's use autocomplete here. Find first 4, but with this rest of the function of the list. So let's call this xs, like this. Okay, then let's go ahead and compile this. GHC 02 OP047 p047.hs and run it with time. And as you see, this gives us the correct answer in about 1.23 seconds. One further note, in order to improve efficiency, we could probably do performance improvements here in this function. For example, we might only need to check until the square root of n, not up to n halves, but in order to keep this program simple, I have not done this here. Thanks for watching.